With a global population of over 7.5 billion people and rising, it's a scary question to ask. How can we continue to feed the world? In the spring of 2019, the Midwestern United States experienced major floods that resulted in major crop failure. At least 1 million acres of US farmland in 9 major grain-producing states flooded. But what if we were able to save 100% of all food grown, and the food we grew could be in our homes, or in areas otherwise too hot or too cold to grow vegetables like lettuce or tomatoes? Hydroponic crops can be the answer to feeding our hungry and growing world population. Unlike conventional crops, where a seed is dug into soil, hydroponic crops are grown almost entirely in water situated in a greenhouse or any closed structure. Using a small inert medium such as gravel, sawdust or sand, the seed is fully submerged in water where everything from temperature, CO2, pH and electrical conductivity are carefully gauged as it grows. The benefits of replacing soil immediately eliminates pests, plant diseases that destroy crops, and weeds. Although you might be thinking that hydroponics would use more water because its soil is compared to conventional farming, only 1/20th of the same water is used, and that's because everything is regulated, recycled, and reused. This creates a more stable and higher crop yield by reducing loss and waste. In addition, the labor involved in upkeeping and mending the plants is reduced significantly. Perhaps the most significant benefit of hydroponics is its advantage to be grown in large urbanized cities where fresh fruits and vegetables can be difficult to come by. In this project, we developed a fully automated hydroponics control system that is compensating the environmental conditions in real time. Our model was built by using MATLAB and Simulink for the tests and the simulations part. To furtherly test our complete system, we simulated real conditions and tried to control the mean environment in our closed hydroponic structure. We used sensors for monitoring the environment, and these include temperature sensors, CO2 sensors, pH value sensors, and EC sensors, where EC stands for electrical conductivity. To compensate against the different and continuously changing environmental variables, we used actuators that helped us with keeping our values at the optimal for each one range. The actuators include a cooler and a heater for compensating the temperature, fans for recycling the air inside the closed structure at where our system was built into, a pH solution for keeping the pH values in range, and of course the optimal amount of nutrients that will keep the electrical conductivity in range. As it was mentioned previously in the video, a hydroponic system should be able to stand up at any environment. So, we had to be able to control high temperatures that might be way above the optimal range of 20 to 25 degrees Celsius, as well as really low temperatures that are close to freezing. To be able to achieve that, we need some strong actuators like heaters and coolers, as well as some kind of thermal isolation for the system. The bottom right graph on the video right now shows the outdoor temperature with a yellow line versus the indoor temperature using the blue line. We can see that by setting an isolation factor greater than 1, where 1 stands for no thermal isolation at all, plus a higher actuator power that is measured in the change of degrees Celsius per hour, we can maintain the temperature at the optimal room temperature range, which is 20 to 25 degrees Celsius, regardless the outdoor temperature, even if that is really high or really low. So we can conclude that our temperature controller has achieved its goal. The same concept of measuring and controlling is followed for all the other sensors and actuators. The goal is the same, and that is to keep our external values at good ranges. Here is the example of the carbon dioxide control mechanism that uses a tolerance of ppm or parts per million, which is the way that CO2 is measured, and this variable is the one which decides whether to turn on or off the fans for air recycling in the system. And here is the complete system. We are able to set desired values for the temperature range, the CO2 levels, the pH and the correct amount of nutrients, and visualize the difference on the plant's growth over a period of 180 days, and that is from planting to harvesting time. Here I have to mention that our team's research was focused to the beef stick tomato plant. A beef stick tomato plant's weight that is greater than 1 kilogram is a successful plant, and that weight includes the root, the shoot, the leaves, and the actual tomato fruit. From the other hand, when the plant's weight is less than 1 kilogram, then this is considered an undergrown or even a dead plant. So we can notice that when we are setting our desired values to the optimal for the tomato plant values, then we end up with a valuable plant. But when these values are set outside the sweet range, then our plant is either underground or dead. Thank you very much for watching. We were Team 15 and that was our fully automated hydroponics control system.